Hello, I'm switching directly to the next talk. I've got two talks of, in theory, 10 minutes, one after the other. So the first talk is about nonlinear optimal power flows in PowSyBl. So my name is Nicolas Omont. I'm Vice President of Operations at Artelys. So Artelys, we are a little bit more than 100 experts, and we are doing both software development, services, and consulting and studies focused on quantitative analysis. So we are specialized in, let's say quickly, we are doing artificial intelligence, and most of the time applied to power systems and to transportation systems. So let's go into the definition of optimal power flow. So I assume some of you know what it is, but not everybody. So optimal power flows is a way to determine the most efficient operating conditions for a power system. So usually you try to minimize the costs of running the system while satisfying system constraints like power balance, voltage limit, and transmission line capacity. So they are really important to optimize the operation and the planning of electrical systems. So indeed, in usual OPFs, you have to model the system, which have buses, generators, power lines, and transformers. So there are several ways to model them, and either you do the equation of the grid are nonlinear. So either you keep this representation of the equation of the grid that represent rather well what can be the equilibrium of the grid, how it's going to work, or you linearize it, and then it's easier to make computations. So tomorrow there will be a talk where we use the linearization to optimize the transfer capacity between France and Spain. But in this quick talk, I want to focus on the nonlinear ones, where we keep the nonlinear equations, which are very important when you want to manage the voltage. And so this very general class of problem is called AC optimal power flows, because we keep the AC equation contrary to the linearized one, which are called DC OPFs. And so as PowSyBl includes a set of tools to do a lot of optimization and simulation of power system. Then it includes also AC OPFs. So it has been developed for a long time, but the first one that is really operational is PowSyBl Open Reac, which is an open source AC OPF. You will find it as a module of PowSyBl. The goal of Open Reac is to what we call it. It was made not to minimize the cost of running the system, but to initialize the voltage plan when you do a power grid simulation. So let's say that you want you forecast the grid state in let's say 2 weeks, and then the issue with that is that you will change the load on the generation pattern, but the voltage plan is likely to stay as it is today or last week, and then it does not work well when you want to compute a load flow or something like that, because the voltage plan has to be adapted to the real grid situations. And in this case, you can use, it's quite convenient to use an OPF to change the voltage plan, to change the generation set point, the voltage generation set point, and to connect capacity banks and like that kind of things. So you can use an OPF with the objective to minimize the losses, for example, and optimize the settings for the voltage regulations. Well, you don't care so much about minimizing the losses, but what you want is something realistic that will allow you to do further studies. So this is why RT developed Open Reac, and we contributed to it. And so what is interesting is by doing it, we developed a basis that for any kind of OPFs. So this is an example, but you can do many other things. So change the objective, add new constraints, and this basis includes a modeling of a wide range of equipment. Basically, most of what you have in PowSyBl is going to be to be used in this optimal power flow. So 2 or 3 winding transformers, static var compensators, HVDC line, whatever. And then you're going to be able to optimize, here in this case, as I told you, reactive set points, tap transformers, and shut sections. Well, the performances are okay for what we need to do. That is on a French IGM with 7,500 nodes. It's going to take a little bit more than 10 seconds. And it has been interfaced, it has been coded in Java, like most of PowSyBl. But as the users need to script it around it, as it was told in other talks, that the tool never do everything. You already need to do pre-processing, post-processing, and the usual power system engineers code in Python. So there is a Python interface so that people can do it. So it's a reusable code base that can be tuned to other OPFs. It's based on a modeler, a model which is written in the IMPL language, which is a modeler that describes all the algebraic equations. And the modeler calls a nonlinear solver that can be Artelys Nitro or any open source solver. And then an important part of it is the converter that converts from the internal format of PowSyBl to CSV tables that AMPL can read. And thanks to that, you can use a power network in any format like CGMES or PSSE or MatPower. So we already used it to do some prototypes of other kind of OPFs, like divergence analyzer that we use to detect errors or any inconsistency in power networks. So it's a kind of optimizer in the sense that you try to, for example, minimize the losses or just find a solution by excluding some data, but by excluding by marking as inconsistent the smallest amount of data of parameters that are given to you, and a state estimator that can detect both gross measurement errors and topology errors. Both of them are published in branches of PowSyBl, but they are not merged into the main tool because they are still prototypes. The roadmap is that we want to do it in Julia Jump instead of AMPL, because for those who know, AMPL is not open source, so that this scheme of ACOPF is not fully open source, which is an issue for PowSyBl. So we want to use Julia Jump instead of AMPL. The work is ongoing. I hope that by the end of the year we will have it. And then with Julia Jump, you will still be able to call Artelys Nitro, or to switch or to use an open source nonlinear solver, so that we will have a full, the best of both worlds, a full open source alternative, and then Artelys Nitro if you want the best performances. Yeah, you see, when you do open source, you've got to make trade-offs somehow, and I mean, we are going to speak of business models afterwards. But indeed, Artelys Nitro is proprietary, and you can mix open source and proprietary and licensing-based business together. I think that this is an example of how it can work. Yeah. And then we are also working to integrate other nonlinear solvers like Artelys Nitro, but also nonlinear solvers, because I mean, we are in an open source framework, so when we do something, there should be an open source alternative to replace the Newton-Raphson of open load flow by an interior point algorithm. And the first results are quite promising. Well, yeah. So we have some. I think I don't have so much time for questions because I think I should finish my second presentation in 5 minutes. But maybe if you have one question. Yeah.
You mentioned the 13 maybe to question on this, what type of hardware was it running on? And also, does this also factor into this all the data conversions that need to happen from the kind of source file to
okay, I don't know the details. For sure, CGMES import is excluded because it takes already 10 seconds, okay? But then, apart from that, I don't know exactly, but it was a normal laptop, and we did not focus so much on the timing. I mean, it's not like a security analysis, you know. Let's say you do a security analysis after that. So anyway, it's going to take 10 seconds for this, and then you're going to spend 5 minutes doing the 1,000 contingencies that you need to do. So this is I don't. Well, the performance was not so much an issue at this level for now. Okay, so I'm sorry, I'm available if you have questions, but then for the sake of being on time, I go directly to the second presentation.